Right now, I'd like to teach you about inclined planes. Basically, the gist with inclined planes is unlike most of the things we've done so far, where we're interested in vertical and horizontal components, because that just made sense because gravity was always vertical, normal force was almost always vertical or horizontal, and it was tended to move in the horizontal plane, possibly the vertical. In this case, our normal force is always perpendicular. A lot of our applied forces tend to be parallel to the surface of the inclined plane, and it's going to tend to move along the surface of the inclined plane. So at this point, it doesn't make sense to switch things into vertical and horizontal. Instead, we're going to make things in terms of into the slope and out of the slope, and down slope or parallel to the slope and up the slope. So this is now what we want to convert everything to. Fortunately, most things will probably already be along those axes, except for one very key one. Gravity always pulls straight down. So we're going to have to break gravity into components. Now, my favorite way to deal with that is to draw it right here. So I'm going to use gravity as the hypotenuse, and I am going to break it into an into the slope and down the slope component. Or I suppose in this one, actually in this one I'm going to need both. So perfect. So this is a more complicated question. So this is my hypotenuse. This is straight gravity. This is m times g, or 15 times 9.8. That will equal 147. Now I'm going to find a parallel to the slope component of gravity, which is trying to push things down slope. And I'm going to solve for a perpendicular to the slope component, which is trying to shove it into the slope. And this one will be 147, or the hypotenuse, times cos theta, because this angle up here will always be the same as the angle down there. Because if you think about it, this is vertical, this is horizontal, so this plus this will always add to 90 degrees. Plus, since this is a 90-degree triangle, going from into the slope to down the slope, these two angles also have to add to 90 degrees. So 26 plus x equals 90, and this angle plus something equals 90. So it'll just always be the same thing. This top angle right here will always be the same as this angle down here. You can do it for yourself, and just no matter what the angle is, you can always be like, okay, well, this plus this have to add to 90, so 90 minus 26, it would be 64, and then these two have to add to 90, so 90 minus 64 gives you 26. So no matter what this angle is, this will always be the same, the top angle there, if you've drawn it in the same way. Anyway, so our theta is 26, and we'll solve for this as well. 147 sine 26, and those are, all right, so calculated that our perpendicular component is 132 newtons, and our downslope component is 64.4 newtons. And our question here is, what force would we have to exert here to make the 15 kilogram block shown below move at a constant speed up the incline? And as soon as I see constant speed, I'm like, oh, my forces into the slope equal my forces out of the slope. So it's not accelerating in this axis, so these two forces have to cancel. My F perpendicular and my F normal, because normal always is straight out. But also, all my forces upslope, which in this case, if it's moving upslope, is just my applied force. And downslope, I've got the parallel component of gravity, parallel to the slope, but I'm also going to have friction. Friction will naturally oppose any movement, and since it's moving upslope, friction will work down. So F parallel, which I just found here, plus my force of friction have got to equal my applied force if it's going to be moving at a constant speed. Because constant speed means the acceleration is 0 because your velocity is not changing. And if acceleration is 0, net force has to equal 0, and therefore all forces must cancel. So we're just going to say F equals F parallel plus force of friction. Apologies for this. Plus force of friction. And so we just plug her in. So we got 64.4 plus our force of friction, which is just mu Fn. And Fn is equal and opposite to F perpendicular. So it's 64.4 plus 0.23 times 132, or 64.4 plus 30.3, or 30.4 rather. 30.4 plus 64.4 will equal 94.8, or when rounded to first sig figs, 95. Right. So they could take a little while to get through, but once you get going, they're not terrible. Like in this case, here's another excellent example. Here we have a frictionless surface. So if we were to kind of free body diagram, technically the free body diagram should look like this. So you got gravity straight down, normal force straight out, and that's your free body diagram. But I like using component diagrams for myself, even though they're not technically free body diagrams. So would not get you full marks on a test. They are incredibly useful. So if I do a component diagram instead of my free body, I will have normal force out here, exactly canceling with the perpendicular component of gravity. And notice F parallel is unopposed, which is kind of interesting. So it's kind of like my net force equals my parallel component of gravity. And my parallel component of gravity, I'll draw my little triangle here. Remember, this top angle is going to equal the same as down there, so that's 34. So M times A is going to equal my F parallel, which to me looks like 4 times 9.8. 4 times 9.8 will be 39.2 times sine theta, because I want my parallel, and that is opposite this. And remember, gravity is my hypotenuse, so that would equal 39.2, my force of gravity, times sine 34. Oh, I could have made it even easier. Why am I even doing this? I could have ignored that. Apologies. So you can do it that way, but there's a nice little trick if you write it like this. Notice my masses cancel. And I've got my acceleration is just going to be equal to g sine theta, which is what you get if kind of F parallels your net force. If your component diagram just has normal canceling with F perpendicular and F parallel unopposed, this is your if and only if formula. If this is true and your diagram looks like this, then you can use this formula, not at no other time. So anyway, it's going to equal 9.8 times sine 34, which is going to be a little bit more than half of 9.8, which sounds like 5.5 to me, but I'll do it just the same. 9.8 times 34 times sine. Yep, 5.5 it is. here's a little quick one. We've got a cart going down a frictionless incline. So basically, the cart is accelerating at the same rate as the ball. So the ball should be kind of effectively weightless. It's a bit of a strange thing. You're going to have to think about it for a while. But basically the gist is if you and the ball are accelerating down at the same rate, it'll just be straight to the top, because along this axis, both the ball and the cart are accelerating at the same rate. So there's no need for anything. Doesn't need to do this, because that would tend to accelerate the ball backwards, but it's accelerating by gravity at the same rate as the cart it's inside, and this is just need to accelerate it versus what would normally be like F perpendicular. And here's another similar one. I'll just do really quick. So if we want the magnitude of the block's acceleration, if we kind of component diagram this, we've got F parallel moving it down, and we've got friction up top, which is just 25. So that's kind of nice. So all we really need to do is find F parallel, and then we can just do a big minus small with the 25. We don't need to bother with F perpendicular because we're already given this, and don't need to use this to find it. So anyway, it's a 6 kilogram block. 6 times 9.8 would be 6 times 9.8 would be 58.8. So that's 6 times 9.8 is 58.8. This angle up top will always be the same as the angle in the bottom. Draw it here if you need to figure that out for yourself. 34 plus this angle have to add to 90. So that would make it 56, and then these two have to add to 90, so that makes it back into 34. So we just need to find our F parallel here, which is just 58.8 times sine 34, because that'll give us the opposite to the hypotenuse. So we go and plug that in. We got 58.8 times 34 sine, and so that'll give us 32.8. So then we can just do a big minus small equals ma. So our big force is F parallel. Our small force is the force of friction, and that's going to equal the mass, which is 6 times a. So we got 32.8 minus 25, which is given to us right here, force of friction, equals 6 times a. 32.8 minus 25 gives us 7.8, equals 6 times a. So it's going to be a little bit more than 1, or 1.3. That's all for today. Thanks for listening. Hope this helped.